Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to give an example of how to kind of combine work energy methods with Newton's second law for circular motion type of problems. So in this example, what we're looking at is this 10 kilogram object is going to start from rest from the position shown. It's attached to this 5-meter long string. And what we're going to do is we're going to try to calculate the maximum tension in this string or rope after this thing is released. So if it's released from rest, we got to think about the motion of this object. It's going to move along a circular path. So the motion diagram might look something like this. Whoops, that's not very good. It's going to move along some sort of circular path down to this position here. And it's important to realize that the tension is going to be the largest when the rope is vertical. So what I'm going to do is I'm going to draw my second picture. All right, so again, what this thing's going to do is it's going to move along this path to this position. The tension is going to be the largest here. I'm going to go ahead and draw the rope. Then I'm going to copy that object and put a picture of it. Enough. Here's a picture, position 2. Now, at that location, the velocity vector would be pointing to the right. Right, so the velocity is going to be this way, but that's not going to be super important for the problem. What I'm going to do here is draw a free body of it at that instant. So if we draw a free body at that instant in time, right, and to draw the free body, I'm going to copy it again. Here's what that free body would look like. We've got the weight of the object down. I'm going to go ahead and put a force vector for that, mg. But we also have a rope in contact with this. That's going to be applying a force up on that object. So I'm going to go ahead and put a force vector in for that. Label it T. Now, you'll notice I made the tension vector longer than the mg. That's because, looking at the motion of this object, it's moving along a circular path. The center of curvature is here. So at the instant shown, this definitely has an acceleration up, which means this vertical force has to be larger than this mg. So the acceleration vector I know is this way. I'm going to go ahead and put that. That's a centripetal acceleration, so it has a magnitude of v squared over r. So we draw our free body. Now I'm going to write a Newton's second law equation. Sum of all forces in the y direction equals ma, up positive, and that's because the acceleration direction is up. Looking at my free body, two forces, tension up, mg down, and then equals ma. Because that acceleration is a centripetal acceleration, it can be written v squared over r. All right, so I'm trying to find the tension. It's a pretty easy algebra problem to find the tension. That's going to equal mg plus mv squared over r. Now the r and the length of the rope are basically the same thing, so I'm going to go ahead and just put L where the r was. Now, as I look at this, you'll notice that the tension is larger than mg by this factor, mv squared over L. And we're going to need the v. Now, specifically what we need is v squared. And although we can't really use work energy to find the tension because it doesn't do any work, we can use it to find this v squared. So I'm going to go ahead and write a work energy equation. However, to do that, we're going to need a datum. I'm going to go ahead in this example. I'm going to do my datum in red here and draw my datum up here just to be different than usual. All right. Now I'm going to call this position 1, this position 2. Now at position 1 there's no velocity, but at position 2 we have a velocity that points this way. I'm going to go ahead and put v2. I guess since there's only one velocity in this problem, we really only need a v is good enough. I'm going to go ahead and write out my work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. Right, potential energies. Now, I went ahead and did my potential energies with respect to a datum up here. That makes both these potential energies negative, which is no big deal at all. PE1 is going to be minus mg Now it's going to be some sort of distance here. The distance we need is this distance right here. The important thing to note, look at this triangle right here. Hypotenuse is 5, this is some distance, this is the distance we need for the potential energy calculation. That height is opposite the 30-degree angle, so that distance is equal to 5 sine 30. So I'm going to go ahead and just put, actually I'm going to put L sine 30 here because the L is equal to 5 meters. All right, KE1 is 0 because it starts from rest. The work term is 0. I'll come back and explain why here at the end of this. All right, PE2 is going to be negative because we're below our datum. mg, and then we need this height right here, which is basically the length of the rope. And then KE2 is 1/2 mv squared. All right, that work term and why it's 0. All right, well, picture a free body of this object. I'm going to go ahead and get it kind of cloned here. Picture a free body at some kind of arbitrary location in the middle, and we start thinking about force vectors acting on that object. The tension would be acting along this path and pointing right towards the circle there. Oops, I do that force vector in black. All right, there's my tension. And in addition to that, we got a gravitational force acting straight down. So these are the only two forces. Remember, motion is not a force. The fact that there's a velocity vector that down and right doesn't matter. That's not a force. All right, so an important thing to realize is which of these forces is doing work. So, ask yourself each force, is this force doing work? And the answer is yes, it is doing work because there's a force and there's a vertical displacement going from 1 to 2. However, that's what the potential energies take into account. So this force is considered and taken into account. Next question, is this force doing work? And the answer is no. And the reason is because the velocity vector at this instant is this way. And that force makes a right angle to the velocity vector. Remember, only forces parallel to the motion do work. So the work done by the normal is 0. So we've considered every force, and this one does work, but that's taken into account with these potential energy terms. The tension doesn't do any work. And that's why that work term is 0. So remember what we want. We want our v squared for over here. So let's add this term to the right and take note that the mass divides out. So we're going to have g times L minus GL sine 30 equals v squared over 2. So v squared is equal to 2g. Well, let's do this. How about 2GL times 1 minus sine 30 is good enough. By time we multiply by 2. And then I factored the GL out because it was just shorter to write it that way. So now anywhere we see a v squared, we can sub this. So our tension is equal to mg plus m over L times v squared, which is 2GL times 1 minus sine 30. And you notice these L's go away, so the tension is equal to mg plus 2mg, and the 2 is coming from here, 2mg times 1 minus sine 30. I'm going to go ahead and put numerical values into this, keeping in mind that the m is 10 kilograms. 10 kilograms times 9.8 meter over second squared plus 2 times 10 kilograms times 9.8 meter over second squared times 1 minus sine 30 degrees. This doesn't have any units because, the sine function is a dimensionless quantity. So I'm going to take a moment and see what I get out of that. I got 196 newtons out of that. Hopefully I ran that right. Just a quick little observation here. Well, if it were just sitting static, it would be 10 times 9 point, it'd be 98 newtons. So, about double that. I think that probably sounds about right for this problem. So Important factors of this problem. One, recognizing that the tension will be a maximum in this position, because that's what I was looking for, is the maximum tension. Two, knowing how to draw the free body. So, picture a snapshot in time. And whenever I draw free bodies, picture, a surface right above this thing's surface. This is how I'm defining my system. You're looking for things coming across that boundary. So that rope comes across the boundary. So there's a force vector for that. The gravitational force is a field force. Right? There's the force vector for that. You need to recognize the acceleration direction. All right, this is undergoing circular motion, so at minimum there's an acceleration towards the center of curvature here. A centripetal acceleration equal to v squared over r. I said at minimum because if we back up and you look at this free body, this thing is moving along circular motion here. So there is a centripetal in this picture that points this way. But in addition to that, there's a tangential acceleration that points this way. You can see it from the free body. You'll notice that this mg has a component kind of down and right, whereas this doesn't. At this instant, though, that's not true. The net force is up. There's only one acceleration at that instant. Next important thing, how to write the Newton's second law equation. So net force is the vector sum of these two. That's T minus mg. And the reason it's T minus mg and not mg minus t is because I'm doing up positive, and that's because the acceleration direction is up. So how to write that Newton's second law equation, very important. Recognizing ruh-roh shaggy, we need the v. So we can write a work energy equation to do that, which I did right here. Now, in my particular equation, I put the datum up top. That made both the potential energies negative. A lot of students may have wanted to, or a lot of people would have maybe wanted to put the potential energy here, which would have made PE2 0, would have made PE1 equal to mg times whatever that distance is, and you need to calculate that distance. That would have been perfectly fine as well. But again, it's perfectly fine the way I did it. You'll notice it worked out just fine. Minus mg L sine 30. The L sine 30 is coming from that distance right there. And again, the hypotenuse is L. Negative because we're below the datum. The minus mgl is because the height here below our datum is basically the length of the rope. Again, negative because we're below our datum. The kinetic energy term is the 1/2 mv squared term for this position. No work because we considered this force and it was doing work, but that's taken into account with potential energies. Then we considered this force, but that force makes a right angle to the velocity the entire time, so that tension doesn't do any work. So net work 0. So the work energy equation is what allowed us to get that v squared equal to the 2gl times 1 minus sine 30. Plug that value here, write your new equation. Simplify it a little bit, put in the numerical values. Hope that this example helped demonstrate how to do these things. Have a great day.